Welcome to this overview of microelectronics and fabrication. Today, we will answer 5 key questions that form the foundation of semiconductor physics. First, how is the band gap of metals and semiconductors formed, and how does it affect electrical conductivity? In solids, atomic orbitals overlap to form energy bands. The crucial ones are the valence band, full of electrons, and the conduction band, which is empty. The energy gap between them is the band gap. Metals have no band gap. Their bands overlap, creating a sea of free electrons and very high conductivity. Semiconductors have a small band gap. This means electrons can be thermally excited across it, creating mobile electrons and holes. This makes their conductivity tunable by temperature and doping. Second, how do we derive the mass action law? This law governs the balance of charges in a semiconductor. We start with equations for electron and hole concentrations. Multiplying them together, we find their product equals a constant involving the band gap energy and temperature. This constant is defined as the square of the intrinsic carrier concentration. Thus, we arrive at the fundamental law. For any semiconductor in thermal equilibrium, N times P equals N sub I squared. Third, what are the characteristics of P-type and N-type semiconductors? Doping changes a semiconductor's properties. N-type material is doped with atoms that provide extra electrons. Its Fermi level moves closer to the conduction band. Electrons are the majority carriers, and holes are the minority carriers. P-type material is doped with atoms that create holes. Its Fermi level moves closer to the valence band. Holes are the majority carriers, and electrons are the minority carriers. Their key similarity is that both obey the mass action law, Np equals Ni squared. Their difference is the position of the Fermi level and the type of majority carrier. Fourth, can we describe the p-n junction's energy band diagram and its conduction properties? A p-n junction is formed by joining p-type and n-type materials. Their energy bands bend at the junction due to a built-in potential, creating a depletion region. Under no bias, the Fermi level is flat. The built-in potential barrier prevents net current flow. Under reverse bias, the applied voltage increases the barrier height and widens the depletion region. This blocks majority carriers, allowing only a tiny leakage current. Under forward bias, the applied voltage reduces the barrier. This allows electrons and holes to flood across the junction, resulting in a large forward current. Finally, what are the mechanisms of avalanche and Zener breakdown? Avalanche breakdown occurs in lightly doped junctions. Under high reverse voltage, carriers gain enough energy to knock other electrons loose through impact ionization, creating a chain reaction. Because higher temperature causes more scattering, carriers gain less energy. So the breakdown voltage increases with temperature. Zener breakdown occurs in heavily doped junctions with a very narrow depletion region. The intense electric field directly pulls electrons across the band gap via quantum tunneling. Here, higher temperature slightly reduces the band gap, making tunneling easier. Thus, the Zener breakdown voltage decreases with temperature. Thank you for watching.